Assalamu alaikum wa rahmatullah. So in this video let me discuss something more on the Young's double slit experiment. Okay, so my objective in this lecture will be fringe width. Okay, in order to know how exactly this fringe width is all about, let me just first of all mention the setup of this experiment. As you know, this experiment involves two slits. This is my slit first, slit second, and there is a screen. Okay, and the screen is at a distance of capital D units from the slits, and the two slits are at a distance of the small d from one another. Okay, this is something that we know from this experiment. And how we define the fringe width, basically the definition of fringe width is like when we use a source of light and the light rays which are allowed to pass through the two slits. Okay, and when the light rays will come and they will just interact. Okay, and due to the interference we have what I can say the successive number of fringes which are going to be formed at some different points on the screen. Okay, that's something known to us from this experiment. But how we define the fringe width, basically we just notify the fringe width by beta. Okay, and we define it the distance between the two consecutive bright or the dark fringes. Okay, suppose if I will draw the line and the point O, it represents the centermost point on the screen. Okay, and if I will assume that here is my bright fringe and here is my dark fringe, this is my bright fringe. Okay, and this is my dark fringe, and this is my dark fringe, and so on. So when we talk about the fringe width, it is defined as the distance between the two successive, or I can say the consecutive bright or the dark fringes. Okay, two consecutive bright or the dark fringes. If I will take this fringe here, it is not consecutive with this, but this fringe is consecutive with this. Okay, so we define the fringe width as the distance between the two consecutive bright or the dark fringes which are going to be formed on some different points on the screen after when we use the source of light here from which the radiations emit, and if the radiations just hit the edges of the slit and we have the light rays, okay, which just come out from the slits and they just show the gloss of disturbance, and such a disturbance is going to be studied as the results we want to know exactly from this experiment, and screen will possess us the kind of that important results and all that. So here when we talk about the fringe width, it's defined as I told you before, the distance between two successive bright or the dark fringes. Okay, it doesn't matter which two successive bright or dark fringes will take, it really doesn't matter, because we'll always get the same result. How? When we just try to express this result in terms of the given parameters that I just draw in the given experiment and all that, just like the distance and the distance between the slits and how far the screen is from the respective slits and all that. Okay, if I will just take this here, the source of light that has some monochromatic wavelength. Okay, that's indeed the requirement for interference effect. Okay, and which has a wavelength of lambda. Okay, and I need to just develop the story in terms of some given parameters, and then after I will just look how exactly my expression for fringe width will look like. Okay, for that what I will do here, I will just use a definition that I mentioned so far here. So choice is completely open here, whether you will take the two successive bright or the dark fringes, you will get the same result here. Okay, for the fringe width. But let me just take the two successive what I can say the bright fringes, and you can just do this exercise for the dark fringes by yourself. Okay, but here I will just make it as a choice of argument for the what I can say for the bright fringes. Okay, when we talk about the bright fringes, means I need to use here the constructive interference condition if I will just assume that if I want to know the position of nth fringe, nth bright fringe from relative to this center of the screen, okay, how I can just look it as it's something that's known to me, and I will just define it. Yes, it's something n lambda, okay, d, capital D or small d, for the symbols for the some usual meaning, okay. This is my position of nth bright fringe with respect to this center, okay. If I will just take the position of another bright fringe, but that bright fringe is consecutive to the, I mean, earlier one, but I will get here n plus 1 lambda d over d, okay. So by this way I go the two positions of the bright fringes with respect to the center of the screen, okay. And how we define the, I mean, the fringe width? Fringe width is defined as the difference between, means that if this is a position of this bright fringe, okay, for the sake of argument I will just take this as my bright fringe here, okay, one of the bright fringe here, it will be yn, and this bright fringe will be here, yes, it will be yn plus 1, okay. Oh, so the distance between these two, it will be yielded when I subtract this distance by this, okay, something that's known to you, okay. So I will do here n plus 1 minus n. I will get exactly what's the distance between these two consecutive fringes, okay. So this is something that I will do here, okay. So yn, I know yn plus 1 is also known to me. I will just make here the simple difference. What I will get here, yes, what I will get here, yn plus 1 minus yn, it will be simply here lambda d over d, that's constant. I will just, that same here, I will just put it out, it will be n plus 1 minus n, okay. This is going to cancel with this, simply I am getting here lambda capital D over small d. So simply I will just opt this value here. This is my expression for the fringe width, okay. Alright, okay, so this is expression for the fringe width, where lambda is the wavelength of the light source and d is the separation of the distance of the screen from the respective slits, and small d is, I can say, the inter-slit distance and all that, okay. So this expression is, I mean, the very important expression, okay. Through the number of ways, we will just come to know how exactly it is important, but in several ways. But here I will do the one simple problem, that's indeed the conceptual problem. What the problem is basically, look, if it is given in a question, we have the source of light. That source of light is known as a sodium lamp, okay. We have the sodium lamp here, which will act as a source of light, and that will give some light rays, okay. After, I mean, when we perform this experiment here, we will get some fringes here, and in case second, what we are going to do, we will just replace this sodium source of light by the blue light source, okay, by the light source which emits the blue light, okay. Blue light source, blue light source, and we need to know what will happen to this fringe width. Will it decrease, will it increase, or will it be same? I will just mention the question here once more. In the case first, if we have the sodium lamp, that will act as a source of light in the Young's double slit experiment, okay. Now in the case second, what I am going to do, I am just replacing that source of light by the blue light source, and I need to know what will be the change in the, what will happen to this fringe width. Will it increase, decrease, or no effect will be observed with respect to this parameter here. How I can do it? Yes, I will for this kind of analysis, I will just look to the equation here. Look, when I am going to replace one source of light with another, for that I'm not just doing any kind of changes in a given experiment. By the way, like, I'm not changing the distance between the slits and distance of the screen from the two respective slits, okay. Means that in both the cases, my d over d, this ratio is going to be constant, okay. When d over d is constant means that my b is simply proportional to the wavelength. Okay. Now it sounds more clearly for me when I'm just replacing my source of light. What will happen here? I can just give an answer to this question with more ease. When we talk about the blue light source, what happens here? What happens here basically, as we know, when we talk about the blue shift, it will lead to the decrease in the wavelength. Okay, remember always whenever you talk about the blue shift, means that there is a decrease in the wavelength. Okay, and decrease in the wavelength means decrease in the fringe width. Means fringes will look more closer relative to one another. Okay, it doesn't matter for me. It really doesn't matter for us whether we talk about the bright or dark successive fringes. Okay, when we talk about the fringe width, that's going to be decrease. Means that two successive bright or dark fringes will be more closer in a case when we use the blue light source, okay, than the sodium lamp source. Okay, my question ends here. The answer of this question is when I'm changing the source of light, taking blue light source instead of sodium lamp, okay, as a light source. So I'm getting the conformation here because I'm not changing these parameters. So I got that idea means that my beta is going to be less for the blue light source. What it into means? It simply means for me the distance between the two successive bright or dark fringes will be entirely lesser in the case second than the first. Okay. So this was something, the good physics content in the question, where we can use this concept and get a very important thing. Okay. Number one. Number two is like that. If I'm just place some slab here in front of one of the slit, okay. If I'll just place here the slab, okay. If it is given that the slab has a thickness T and it has a refractive index of mu, okay. Now, if I will just use here source of light and the light will just allow to pass through the holes, okay, and it will just hit the screen here, and there is one more light ray here that will hit the screen, and we have the pattern like this. Okay. Okay. Now, how we can proceed our analysis here in order to know what will happen to this fringe width? Look, just focus on the given information here. If I'm just placing the slab here whose refractive index is given and whose thickness is given. If I will use here the glass slab, means that its refractive index, I will just represent it with the mu g. It has a thickness of T units. I'm just placing this glass slab in front of the slit first. Okay. Now, under the situation, I need to know what will happen to the fringe width. Okay. What will happen to the fringe width? How I can just look for this kind of result. For that, I should know once more here what will happen to the fringe position. Will it be same or will it be, yes, different? Means that the moment when I'm just removing the glass slab here, I will have the position of fringe, okay? And then after, if I will just place the slab in front of one of the slit here, what will happen to the position of the fringes? Will it be at the same position or will it be different? It is something that I need to look for here. How I can just look for this kind of analysis here? Look, as you know, when we are just performing the double slit experiment, we assume that the medium we have between the slits and the screen, it is purely an air medium. Okay, we can perform the double slit experiment in any other medium also, but in order to simplify or everything, we at the first place we are presuming that the medium that we have, that we introduce between the slits and the screen, that's purely an air. Okay. Now, what we are going to do, if I just place this, here the slab whose refractive index and the thickness is given. Okay. Under this condition, I will just look for the position of the fringe right now, where it is going to be formed. Will it be formed at the same spot or somewhere different? That's key here that I want to look for. now how I can just look for this kind of analysis here. For that, look, when we talk about S1P, how I can just calculate this much of, I mean, the path length here, S1P. Yes, how I can calculate it? Yes, let me just look here. I will just mention this path here by L1. Okay, my L1 will be simply here. Yes, it will be S1P minus T, means that the path length covered by the light ray. Look, the slab, it has a thickness of T. Now this much of length means that the light ray S1P has to be traveled in air. Okay, plus the path length it will cover in the medium like slab. Okay, means that it has to cover the length or the thickness equivalent to the, I mean, that's given for a given slab. Okay, now this is something that seems more, I mean, clear here, that whatever distance that's pending here, that's S1 minus P, S1P minus T, it's a distance that the light ray has to be, I mean, travel from here to there, and this much of distance involves air as a medium. Okay, and this much of distance involves another medium, that's a glass. Okay, so hope you are getting it. It is a very easy, I mean, thing here to understand. Like, the total distance here is L1, but this involves two mediums. One is air, another is in the glass medium. Okay, so for that, what I will do here, I will just look for the distance that light need to travel, this light ray. Okay, that it needs to travel in the air, like that will be this much or this much. Okay, it will be simply S1P, that I will subtract it by T, and this much of distance that light need to travel, it involves air as medium, plus this much of distance that it need to travel involves another medium. Okay, hope you are getting it. Okay, if I'll just do it once more, if I'll do one more step, L1 will be simply S1P minus T air plus T of slab, it will be simply mu times T of air. Okay, yes, so I can write my L1 here. Yes, S1P plus, yes, mu minus 1 T of air. Okay, means the distance that the light ray need to travel along this medium, it will be simply, yes, refractive index times the distance, the same distance that it will need to travel in air. Okay, this is something that's, I mean, the very simple here to understand. Okay, this is the path length for light ray first here, and the path length for the light ray that passes through the slit first. Okay, now the path length for the light ray that passes through the slit second, that's L2, it is simply S2P. Okay, now my delta L will be simply here L2 minus L1, okay, L2 minus L1 means that delta L will be simply here S2P minus S1P minus mu G here minus T. Okay, yes, look, S2P minus S1P, it's a usual part difference. Okay, so I can just write it as del minus mu G minus 1 into T. Okay, so here what I am getting basically, yes, or I can write my del, it will be here. Yes, if I want to know the position of any order fringe, of any order, I can just write it as d y n or d minus mu G minus 1 T. Okay, this is something that I got from the given analysis and all that. Okay, means this is a position of fringe of any order. Okay, so obviously this is something that I got at the first moment when I'm just look for the description in the Young's table select experiment, but don't look for exactly whatever the don't look for any kind of new thing that's going to be in front of any other slit. Okay, and obviously there is a shift in the position of the fringe. There is a shift in the position of the fringe by this much. Okay, means that the fringe, the position of fringe as in the case without the slab is right now different as if in the case with the slab. Okay, by it is going to be shifted by this much. Okay, so for that if I will just try to analyze what will happen to the fringe width. Okay, what will happen to the fringe width, how I can just calculate it. Yes, if I look for the fringe width, it doesn't matter, it really doesn't matter for us whether we talk about the position of successive bright or the dark fringe. Okay, it really doesn't matter for us because we will always get the same result here. So let me just try to analyze this case when we talk about what will happen to this fringe width if I will just look the consideration of this thing here. Okay, if I will just use any other condition, whether destructive or the constructive interference, okay, it really doesn't have any effect on the fringe width, because fringe width is defined as the distance between the two successive bright or the dark fringes. Okay, choices completely open here. You can take the interference constructive or the destructive condition of interference here. Let me just take here for the sake of argument as the constructive one. For that I will get here dyn or d minus mu g minus 1 into t. It's some n times lambda. Okay, this is meant for the constructive case. So if I will just try to know my yn, it will be simply here. It will be here d by d n lambda plus mu g minus 1 into t. This is something that we will get after using some kind of transformation to this equation. Okay, it's not a big deal here. I'm getting this equation here. It gives me the position of nth bright fringe. Okay, it is something different in the case when there is not any kind of slab in front of any of the slit and all that. Okay, now if I want to know the position of another successive bright fringe, that's n plus 1 or n minus 1, it really doesn't matter, because if I will take n minus 1, but I will just use here n plus 1, because I told you it really doesn't matter, because the two fringes should be consecutive anyway. Okay, but when we talk about the dark fringe, you should take consecutive dark fringe, but here it's a bright fringe, you should take consecutive bright fringe. Okay, so it will be d by t. Here it will be n plus 1 lambda plus mu g minus 1 into t. Okay, so you can just look here the difference once more, because beta is defined as the difference of two consecutive bright or dark fringes. So what I will get here I will get here my beta, it is yn plus 1 minus yn. It will be d or d n plus 1 plus lambda plus mu g minus 1 into t minus n lambda minus mu g minus 1 into t. Okay, this is something we will get after subtracting the positions of the two fringes. This will go with this. Here I will have left with this d over d. It will be n plus n lambda here plus lambda minus n lambda. Okay, so this will go with this. Simply I am getting here again what I can say, lambda d over d. Okay, so there is no change, no overall change in the what I can say, the fringe width. Okay, it doesn't matter, really doesn't matter in case of the fringe width. Okay, and this is indeed the beauty of this fringe width. I'm just placing the slab who having some refractive index and some thickness. Okay, it really has no effect on what we can say the fringe width. Okay, so fringe width remains the same in case if I am going to place what I can say the slab in front of any of the slit and all that. There is no effect on the fringe width. Okay, but the position of fringe is going to be changed. Position of the fringe affects, but it has no effect on what we can see the fringe width. Fringe width is same, means beta is same here. Beta is same as before. Okay, so this was some related facts about this fringe width. Okay, how we define it, and there is no appreciable effect. There is zero effect on fringe width by introducing any of the by introducing the slab in front of any of the slit and all that. Okay, I'm just placing it here. You can just place it here and just look for the path difference here once more, and you will again get the same confirmation, because this will cut here again and you will get again this kind of result here, that you can just state it in that particular case also, that there is no such effect observed on fringe width. Okay, even if we are just placing the slab in front of any of the slit in the X double slit experiment, but it has appreciable effect on the position of the fringes on the secant. Okay, this was something about some good remarks about the fringe width in the Young's double slit experiment. Thank you.